Hello. Today we'll be talking about the geometric interpretation of what it means to be an eigenvector. An eigenvector, as you may have learned in class, is a vector V such that when you apply the matrix A to it, all you get back is the scale factor lambda times the vector V back. This scale factor is called an eigenvalue. So that's what it means in an algebraic sense to be an eigenvector. But for a geometric sense, we might want to take a step back and see what the matrix A does to a general vector V. So let's consider a matrix A. Let's say 5/4, 3/4, 3/4, 5/4. And let's take a vector V. Let's say V1. And this vector V1 will be 8 minus 4. Now I'm going to let you have a second and do a V1 on your own time. Okay. So, if you did it right, AV1 should have been 7, 1. So, let's go to the graph and see what A has done to V. So, the vector V1 is 8 minus 4. So that means we need to go over 8 and down 4. And V1 will point to that point. AV1 is 7, 1. So that means we need to go over 7 and up 1. Right? And you can see that V1, after you apply the matrix A, has rotated and shrunk. So what you can see is that matrices, what they do to vectors, is they rotate and shrink or stretch vectors to generate new vectors. So let's consider another vector and see what A does to it. So let's consider a vector V2. Let's say it is 3, 3. Now I'm going to give you another chance to do a V2 on your own time. Okay, so if you did it correctly, a V2 should have been 6, 6. You may have noticed that this value, this vector, is 2 times 3, 3. Which is just 2 times V2, which correlates exactly with what it means to be an eigenvector in an algebraic sense, right? So A V2 is just a constant times V2 back. So let's see on the graph what this looks like when I apply the matrix A to V2. So V2 is 3, 3. So we go 3 over and 3 up. And this is V2. And AV2 is 6, 6. So that means we need to go over 6 and up 6. So go 6 over 6. And this is a V2. And we can see that V2, after you apply the matrix A to it, has stretched by a factor of 2 and has not rotated at all. So, eigenvectors in a geometric sense are vectors for which, when you apply the matrix A to it, they do not rotate but only stretch or shrink. So, just to get that idea further in your minds, let's do another example. So let's say I'll take V3, and this is 4 minus 4. And I'm going to do this matrix multiplication for you. So AV3 is 2 minus 2, which is 1/2, times the vector V3, which is 4 minus 4. And when we look at the graph of V3 and AV3, right, we can see a similar idea to the case of V2. So V3 is 4 minus 4, so we go over 4 and down 4. And AV3 is 2, 2, so we go over 2 and down 2. And that should be AV3. And just like we expect, the vector does not rotate, but only is cut in half by a factor of 2, right? So it shrinks by a factor of 1/2. So we can see that eigenvectors for sure do not rotate when you apply the matrix A. And we can see something even deeper here. We can see that the vector V1 starts to rotate into the direction of V2. Well, let's wonder why that's the case. So there's two types of eigenvectors. There are reinforcing eigenvectors, and these are the eigenvectors where the magnitude of their eigenvalue is greater than 1. You can see that AV2 has an eigenvector of 2. Surely that's greater than 1. And diminishing eigenvectors, where their eigenvalue has a value less than 1 in magnitude. And you can see here that V3 has an eigenvalue that's 1/2, and in magnitude that's less than 1/2, and that's less than 1. So what you can see here is that vectors like to go in a direction that is reinforced. So V1 will go towards the reinforced direction, which is V2, and away from the diminished direction, which is V3. So that encapsulates the basics of the geometric interpretation of what it means to be an eigenvector. I hopefully will see you next time, and have a good week.